Today we are walking through the paper titled Small Scale Experiments. Are we there yet?
Can we start with the big picture?
The paper asks whether researchers really need huge models to learn how models scale. Its answer is optimistic. Scaling laws can appear in models as small as 4 million effective parameters, but only when the hyperparadigms are tuned thoroughly.
What made earlier small-scale studies look unreliable?
Earlier work reached conflicting conclusions about how parameters and data should grow, and later surveys found small model scaling laws hard to reproduce. The cost problem made this worse experiments.
So what is the paper saying was confounding the scaling signal?
Hyperparameter quality. A scaling law describes the best attainable loss for a given model size and data budget. If small models are evaluated with mediocre settings, the measurements mix the scaling trend with tuning error.
How can the experiments tell whether the tuning search was good enough?
The paper uses a noisy quadratic limit. Near the optimum, validation loss behaves like a low-dimensional quadratic surface plus noise from random seeds. That gives a statistical test for whether random search has reached the asymptotic region around the best configuration.
What does the first equation mean for the tuning search?
Equation 1 models the validation loss at a hyperparameter setting. The optimum is y star at x star, the Hessian describes the local curvature, and d is additive Gaussian noise. The point is practical curvature tells us how sharply performance falls away from the best setting.
And how does the paper connect that local picture to random search results?
The second equation describes the lower tail of scores collected by random search. Its parameters summarize the best attainable performance, the concentration around that performance, the effective number of hyperparameter directions, and seed noise. A fitted tail can therefore reveal tuning difficulty without estimating every Hessian directly.
Before the results, what scaling law are they trying to estimate?
The usual joint scaling law relates pre-training loss to effective parameters beyond training tokens t. Epsilon is the irreducible loss. It is a law for the fully tuned frontier, not for arbitrary hyperparameter choices.
Why does compute make this a trade-off rather than a simple race toward larger models?
Because the compute is proportional to parameters times data. With a fixed budget, spending more on model size leaves less for training tokens. The scaling law condition balances the parameter term against the data term, then turns both choices into power laws of compute.
What did the authors actually run across the different scales?
They sample hyperparameter configurations across effective sizes from about 4 million to 268 million parameters. The smaller sizes form the training range, the middle sizes are validation, and 268 million is held out for the test. They use random search in the warm-up stable decay schedule. Branching decay runs from checkpoints, so one sweep covers several token budgets.
Which part of the methodology mattered most?
The ablations separate refinements from necessities. Parameter count definitions change the estimate only a little. Tuning separately for each parameter and date a budget improves precision, and learning rate decay improves it further. But the decisive ingredient is reaching good configurations in the first place.
Can we see how those methodological refinements change the fitted law?
The methodology comparison shows a recognizable scaling trend from the start. Refinement makes extrapolation more accurate. Tuning each parameter and date a budget cuts test mean squared error by 50%, and learning rate decay cuts it by 98%. Tying the exponents is inconsistent, improving tests slightly but hurting validation.
So what happens if the search simply does not try enough hyperparameter settings?
The tuning budget comparison makes the failure concrete. With 4 configurations per scale, the law is absent. At 16 it is still buried in noise. At 64 it becomes visible but remains imprecise. Only 256 configurations produce an accurate law.
Why does increasing model scale make the search easier?
As scale increases, random configurations occupy a larger near-optimal region. The score distribution concentrates around the best achievable loss. This is why larger models can be easier to tune even though they cost more to train.
Is this only a change in the average loss, or does the geometry of the tuning problem change too?
The geometry changes. The effective hyperparameter dimension, gamma, falls as parameter count grows and approaches 1 in the large model regime. Increasing data has a weaker effect, so the small-scale surface is higher dimensional and unforgiving, while the large-scale surface is gentler and easier to navigate.
What does it imply for how researchers should design small experiments?
The paper recommends a holistic workflow. First, keep the pre-training data fixed so loss can proxy capability. Second, search hyperparadigms rigorously enough for the scaling law to emerge. Third, use the easier large-scale regime only for the final transfer, while checking each assumption as a diagnostic.
What is the main warning about extrapolating to far beyond the measured scales?
Extrapolation magnifies sampling error. Near the observed data, independent scaling law fits agree well. Far away, they mostly compare estimates of irreducible loss, and those estimates vary substantially across samples. The law can exist without giving enough statistical power to rank distant models confidently.
How do they demonstrate the workflow on a concrete modeling choice?
They revisit where to place normalization layers in a transformer, before the sublayer, called derenormalization, or after the residual connection, called boost normalization. The choice wants the gears to settle, so it is a useful test of whether affordable experiments can recover a large-scale conclusion.
Was the comparison affordable enough to use many configurations instead of just a few large ones?
Yes, they fit the comparison on for M and third I for M models, because compute scales roughly quadratically with model size when parameters and tokens grow together. 1 billion parameter run costs about as much as 60 for runs at 100 third I for M, 1024 at 30 for M, or 65,536 at 4M.
What did the diagnostics reveal about the two normalization choices?
Derenormalization was easier to tune. Its noisy quadratic regime appeared more readily. Both choices became less sensitive with scale, but post-normalization retained a large subbottom peak. That means the transfer problem is not just about which architecture can win in theory, but which one can reliably reach good settings.
Did pre-training loss still tell them something about downstream capability?
With the pre-training data fixed, yes. Across scales and across the two architectures, models with the same pre-training loss followed a common capability trend. That lets the researchers compare architectures through the cost of reaching a loss, without pretending that every downstream task has its own predictable scaling curve.
And what conclusion did the scaling law comparison support?
Derenormalization scaled better over the measured range, especially where the data directly supports the law. Post-normalization could look better only under a distant extrapolation that assigns it a lower irreducible error, which is statistically fragile. If both eventually reach the same final loss, the derenormalization advantage remains.
What are the limits of the small-scale premise?
The evidence is strongest for model-centric research with fixed data. Changing the pre-training data breaks the loss to capability correspondence, and extrapolation still has statistical limits. So small experiments need judgment and multiple diagnostics. They are a rigorous microscope, not a crystal ball.
So what is the one idea we should carry away?
Small-scale experiments were not failing because scaling laws were absent. They were failing because the small model frontier is difficult to reach. Search broadly, test the statistical assumptions, trust comparisons near the data, and use the resulting evidence to guide the scale up.
So the practical lesson is to spend the search budget where small models are most sensitive, then scale the validated choice with care.
That wraps up this paper walkthrough.